when we try to solve extensive form games, the key thing or the key step is writing the set of strategies for each player. All right? Because if you're not clear about the strategies of the players, trust me, you will never be clear about the outcome. It's the equilibrium, Nash or not. So first things first, writing strategies down correctly is the key thing, right? You have to clear that first. Well, the definition, I spend like hours in my videos to describe what strategy means. So it's really important. But let me repeat, a strategy in an extensive form game is basically a function, right? Which maps each decision node or information set of the player to an action available at that info set. All right. Well, here, player 1 has 2 decision nodes, 1, 2. All right? So therefore, his strategies should be tuples. His strategy should tell us what he's going to do at every decision node he has, and he has 2. So how many available actions he has in his first decision node? 2, left and right. So therefore, he's going to have one strategy starting with left and another strategy starting with right. I'm going to put them into parentheses. Sometimes I don't. And in fact, later I am not going to use parentheses because, there's no point of doing it. I just wanted to separate them. Well, in his second decision node, he has 2 actions, H and T. So I can put H here and also T. So then I need another L because LT is a combination, LH is another combination. And here RH and therefore RT is also a possible combination. So all possible combinations of his strategies at every decision node player 1 has. So player 1 therefore has 4 strategies. So this is S1, comma, all right? What about S2? It's very simple. He has only 1 decision node. So therefore, it's not going to be tuple. It's either U or D. I mean, again, you don't need to put the parentheses or the brackets, but I'll do it just for now. So these are the strategies. Okay? Well, how do I solve this game? I mean, what does it mean? It's like, what is the equilibrium or solution concept we have up until this point? We have a strictly dominant strategy, right? Iterated elimination of strictly dominated strategies. And we have Nash equilibrium. So we can find the Nash equilibrium of this game. How are we going to do that? Well, it's not so easy to see the Nash equilibrium in this when the game is in this fashion. Remember we said this game should be strategically equivalent to, what we call it normal form representation of a game. All right? So the normal form representation of a game is this. We look at the strategies of the players. Player 1 has 4 strategies. So it's going to be 1, 2, 4 rows. And player 2 has only 2 strategies. So there's going to be 2 columns. So I'm going to put the strategies here for player 2 and strategies of player 1 here. LH, RH, LT, and then RT. Okay? Well, then I'm going to fill the boxes by just, following those strategies on this game tree. Well, for example, what is this box going to be? LHU. Well, the first player is, so don't forget here, the order matters a lot, right? The first thing, the first action is telling me what action he's going to take, player 1 is going to take in his first decision node. Okay, so he's going to play left. Then H is irrelevant, U is irrelevant. The payoff, the game is going to be over, so the payoff is going to be 1-0. And here as well, because it really doesn't matter whether player 2 plays D. And in fact, LT also going to lead to the same payoffs, 1-0. However, when he plays R, for example, RHU, okay, player 1 plays R, and then H, yeah, but we first need what player 2 is going to be playing. Is it going to play U or D? U, because I'm trying to find the payoffs here. So therefore, it's 0, 1. And RHD, okay, so player 2 is playing D, R, D, and then H. Now it matters. It's going to be 1, 0. Okay? And then let's fill this out. RT, R and here, T here. U, RU, again 0, 1. And then finally RTD, RTD, so it's 1, 2. So we say this is an assumption, right? It makes sense, but again, assumption, it's not a fact. So we say these two games are strategically equivalent. Okay? Well, why is that so? Well, we kind of think this game as follows. These two guys look at this game, player 1 and 2. Player 1 envisions what the roadmap he may be following in this game. He may play LH, meaning he basically play L and finish the game. Or he may play R, for example, RH. But obviously, the outcome depends whether the second player is going to play U or D. So the thing is, I have those strategies. Obviously, LH, LT makes no difference, right? Because I'm going to finish the game immediately at the beginning of. So it really doesn't matter whether I assign H or T in my second decision node. So you may say, why do we really have two different strategies here? Why not just one? This is just mathematical convenience, trust me. It's going to make our life easier. Not in this game. I know it's counterintuitive in games like this, but in more complicated games, it actually makes our life easier. Because if we have this, we can say strategy is a function which maps each decision node to an action available at that decision node. If we don't have, if we say, well, LH, LT must be combined as a single strategy as L, well, then our definition of strategy is going to be more complicated. So no point. So let's leave it as is. Well, the first player is going to think, well, these are my strategies. So at the very beginning of the game, what would I choose? Would I choose to follow this path or this path or this path? So similarly, player 2 thinks before the game begins, should I follow U or D? Depending on my opponent's play, obviously. But the thing is, here it's simultaneous move game. Here it's an extensive form game. But the way we solve extensive form games is as if they come together, they choose their strategies at the beginning of the game, and then once they choose those strategies, they insert those strategies into a robot, and the robot plays the rest of the game for them. And the thing is, I should give a break, I know. Let me just say one more thing. Our equilibrium concepts are going to be what we call, I forgot the word. When you choose a strategy, you shouldn't revise your strategy. All right? So when we look for a solution, that's one of the important properties of a solution of an extensive form game. All right? So the optimal solution in an extensive form game is a strategy for each player where they do not need to revise that strategy as the game unfolds. All right? So that's sort of an implicit assumption we have. Because if you're going to choose a strategy today, optimally, and then 2 days after, or 2 steps after, you change your mind and say, hey, you know what, this is no longer an optimal. Well, then your initial strategy wasn't optimal. Because there's no information changed up until this point. Everything is stable in this world. You knew the payoffs, you knew the opponents. You just didn't know your opponent's action, but nevertheless, as a rational person, you should have guessed correctly. All right, so this is what we are going to mean optimal solution in an extensive form game. And so that basically boils down why we have strategic equivalence between these two games. And so we basically find the Nash equilibrium of this game and say, well, it's going to be a solution of this game.